Alright, good afternoon, POE. Here we go. We're going to keep things going as quickly as possible and get you through the material that I have left, which is Unit 4. Some of it is going to be my building. You may want to download Robot C at home. You have the ability to go to My PLTW software and scroll down until you find POE Robot C, and you should be able to download a version at home. Alright, so Unit 4, probability is our first thing we're going to look at. So this shouldn't be something new, this should be something that you've learned in math, but this is a review. So I know as kids you played board games, all based on probability. Hopefully the game you played wasn't called I Win. My son and daughter are both very good at that game. So there's empirical probability and theoretical probability. So one is based on process control, the other one is based on we know the elements. And then we have subjective probability also, which is assumptions. How many times have you heard somebody say, I think that, ... That would be a subjective assumption. So an experiment, all it is an activity with an observable result. So you've all done experiments. And then a sample space is a set of all possible outcomes. And then an event is a subset of that sample space. So for an example, flipping a coin, if I want to know the outcome of 10 possible outcomes, each time I flipped it would be an event. And then we have our outcome or our sample point, which is the result of an experiment. So what is the probability of a coin toss landing heads up? Well, let's have an experiment. Yay, we're flipping a coin. Look at those awesome Project Lead the Way graphics. Of course, we never see if it's heads or tails. And that's enough of that. So we have a probability tree. Probability tree has two outcomes. First outcome is heads. Second outcome is tails. That would be an event. So if heads is flipped the first time, our outcome is heads. We have communicating belief that an event will occur. So we can use 0 to 1, we can use fractions, percents, decimals, and odds. Total probability of all possible events totals is 1. So n is the total number of events. Here's our relative frequency formula. Here we go. Total number of events with outcome of x, frequency with outcome of x, total number of events is n. So we have fraction, percent, decimal, or odds. So there's a 100% chance that I'm not going to see you until at least April 3rd. That's an example of probability. Total frequency of all possible event totals equals 1. So how many desired outcomes are there? How many possible outcomes are there? Look at our probability tree. Desired outcomes, if we want heads, is 1. Possible outcomes is 2. So then here's our formula again. P, so the probability is 1/2. 1 out of 2 times will I get heads, or 50%, or 0.5. So this is the way we show probability. So the probability of the Browns winning the Super Bowl, we change this to a 0.0005, which would make this less than 1%. Just throwing that out there. So probability of tossing a coin twice and it landing heads up both times. So how many desirable outcomes? Still 1. Because there's only one way to get heads on your first flip, heads on your second flip. How many possible outcomes are there? That would be 4. Because we have our first flip and then we have our second flip. So you have a 25% chance, or 1/4, or 0.25% chance, or 0.25, that this is going to work out in your favor. So what is the probability of causing to turn 3 times and it landing heads up exactly 2 times? Okay, this is where it gets exciting. So we have heads versus tails in our first flip. Heads versus tails, Heads versus tails. We're still not out of the weeds here yet because we have one more flip and one more opportunity to end up with heads. This is totally out at this point. Third flip. So heads, heads, probability of the coin 3 times, exactly 2 times heads, so this is out now. However, this one's in, so there's 1, 2, 3. So desirable outcomes, we have 3. Possible outcomes, 6, 7, 8 is 8. So 3 over 8, or 37.5% chance of getting what we want, which is exactly 2 heads. Each trial has only 2 possible outcomes, yes or no, on or off, right or wrong. Tossing a coin does not affect future tosses. So if I toss the coin the first time and it lands on heads, that has 0 impact on the second flip, and the third, and so on and so forth. So Bernoulli process, probability, number of times for a specific outcome within the trials, number of trials, probability of success, probability of failure, and then factorials. So what is the probability of tossing a coin 3 times and it landing heads up 2 times? Well, we already figured this out. 3, 2, 1, 0, 5, 0.5, 2 over 1, 1 over 1, 37.5%. So that is basically how they come up with that 37.5%. Law of large numbers. The more trials that are conducted, the closer the results becomes to the theoretical probability. So if I flip a coin 5 times, and these are heads, tails, heads, heads, tails, 60% of the time somebody says it's going to end up on heads. Okay? Now if we change that and flip it 500 times, how many times does it land on heads? Almost exactly half, which is closer to the theoretical probability of 50%. So total possible outcomes 2, 50% of it will be heads. And then we have independent probability. So here we go. The probability of rolling a 4 on a single-sided die. How many desirable outcomes are there? How many possible? Desirable is still 1. Possible is 6. So we have 1/6. Now what is the probability of rolling a 1? Still 1/6. What is the probability of rolling a 4 and then a 1 in sequential rolls? So we have our probability of 4, our probability of 1, 1 over 6 times 1 over 6, 1 in 36 chance, or 2.78%. For those of you that have ever seen anything on Vegas, Vegas loves probability. This is the reason. 2.78% chance of winning. And then we have OR, which is addition events. So events A and B are mutually exclusive, then the probability of A or B occurring is, there's our formula, so the probability of rolling a 4 on a single die is still 1 over 6, 1 on a single die, 1 over 6. Probability of rolling a 4 or a 1 on a single die. Now we're 1 over 6 plus 1 over 6, which is 2/6, which now we're at 33.33% chance. Big difference in our probability number here. And then not, what is the probability of not rolling a 1 on a die? 1 minus 1 over 6. We now have an 83.33% chance of not rolling a 1 on a die. So then we get into cards. So we have 2 cards are dealt from a shuffled deck. What is the probability that the first card is an ace and the second card is a face or a 10? Please don't do this with euchre cards. That's cheating. So how many cards are in the deck? 52. How many aces? 4. How many face cards? 12. How many 10s? 4. So what is the probability the first card is an ace? You have 7%. Remember, when you're dealing with fractions, you need to reduce. 4 over 52 is not acceptable. Since the first card was not a face, what is the probability that the second card is a face card? Now we're down to 12 over 51. because there are 12 outcomes. 4 over 17. Notice, this isn't 52 anymore. Since the first card was not a face card and it's not put back in this deck, now we're down to 51. Second card is a face card, 23.53%. Since the first card was not a 10, what is the probability the second card is a 10? Now we're looking at a different one. We're still down to 51 out of 52, so these are exclusive events, 7.48% or 84%. So now 2 cards are dealt from a shuffled deck. What is the probability the first card is an ace and the second card is a face card or a 10? So 1 out of 13, 1 out of 13, 16 out of 51, 2.41%. So that's given that the first card is an ace and the second card is a face or a 10. If the first card is an ace, what is the probability the second card is a face card or a 10? 31.37%. Then you have conditional probability. Probability of event E, given that event A has taken place. 1 card is drawn from a shuffled deck. The probability it is a queen is 4 out of 52 or 1 out of 13. However, if you already know it is a face card, now you're down to 1 out of 3. Probability of 2 events A and B occurring. If A and B are independent, then probability of A and B equals P of A times P of B, and you get this wonderful, wonderful formula here. So, an example of how this theorem is in place. LCD screen components for a large cell phone manufacturing company are outsourced to 3 different vendors, A, B, and C. A supplies 60%, B supplies 30%, and C supplies 10% of the required LCD screen components. Quality control experts have determined that 0.7% of vendor A, 1.4% of vendor B, and 1.9% of vendor C are defective. The cell phone is chosen at random and the LCD screen was determined to be defective. What is the probability that the LCD screen was produced by vendor A? So, probability defective A, B, and C denotes the vendors, unknown to be calculated. Probability of A given D. Probability the screen is from A, given that it is defective. So, what known probabilities do we have? 60% for A, 30% from B, 10% from C. Now we look at our known conditional probabilities. 0.007 or 0.7% given A. Probability that it is defective given B, 1.4%. Probability from C, 1.9%. So we plug it all into this theory, or theorem. Screen is defective and from A. Screen is defective from anywhere. So 0.6, 0.007. We throw that into this equation also. So we come out to 40.78% chance that it's from A. So if a cell phone is chosen at random and the LCD screen is determined to be defective, the probability that the LCD screen was produced by B and then also by C. So all those can be done. So what I'm going to do is I'm going to drop the assignment in for you today, along with I put the engineering notebook template in so you can print those out at home. We're still going to keep business as usual on those. If you can scan and submit those in an email each Friday, have 5, that would be great. Continue to keep up the good work, guys, and be great.